Welcome everyone to this Design World webinar on best practices for motion control, stepper motor, and encoder selection. I'm your host, Leslie Langnaw, Managing Editor of Design World Magazine, and joining me today are Ryan Line, Vice President of Operations, and Mindy Chang, Project Manager of Lin Engineering, and Jim Stevens, Vice President of Sales and Marketing, and Josh Barton, Business Development Account Manager of US Digital. If you have any questions during the presentation, please enter them in the questions section, and we will get to them at the end of the presentation. And with that, we will begin with Lin Engineering.
Hello, everyone. Good day. This is Ryan Lin from Lin Engineering, and welcome to the webinar hosted by Design World, Lin Engineering, and US Digital. So today we're going to go over best practices in designing a step motor and an encoder selection. We're looking at selecting a step motor, common step motor enhancements, take a look at a case history, and then US Digital will take over talking about benefits of an encoder and encoder selection. So what I wanted to do today in terms of selecting a step motor is not go over what you might pick up in a physics books or in the off the internet in terms of calculating torque and loads and so forth, because we can do that all the time, but I want to do something that you can take home with value, some actionable item that you can take home into your designs today. Many people can look at torque and maximum efficiency, but what we want to do is use your motor to measure the torque. And we'll do that, and then we'll look at power available, how much power you have available, and then look at common issues for design, including resonance and accuracy. Okay. So let's say you could use a 3D CAD system to measure your torque and your loads. It won't be exact because sometimes you won't know the friction, you won't know the inertia exactly. So the technique that we've used with a lot of customers, and it's proven to be very successful, and I'd like to get feedback from you guys after you listen to this webinar on whether or not it's effective for you guys as well. What we do is you take a motor that's in an existing system, and you will increase or decrease the voltage and current. You want to change only one or the other. Now what happens is when you do that, if you look at the torque speed curve on the right-hand side, you'll see that the left-hand side on that curve is torque in ounce inches, and the bottom axis, or the x-axis, is in speed in pulses per second. So if we look at 4,000 pulses per second in the red line, you're about between 135 ounce inches per ounce inches at that speed. That's at 48 volts. So if you increase your voltage or decrease your voltage, you're going to get varying torque. You will find your system to stall or work perfectly depending on where your design point is. And if you take that information and then you take the speed and the voltage that you changed, or current, whichever it is, only change one of them, and feed that back to your step motor manufacturer, the step motor supplier will be able to back calculate what the torque is required. So let's say in this application you had to reduce it down to 36 volts, then the step motor supplier could take that curve, take that red curve on the right-hand side, and run the torque speed curve at 36 volts and see what the torque output is at 4,000 pulses per second. Then you can design what your torque margin should be, or design a new system in a new application. So here's an example where a user is using the motor to design from an old operating speed to a new operating speed. So they want to go from 600 pulses per second at the bottom x-axis, and they want to move to 1,000 pulses per second. They couldn't change their voltage. At the top of the graph, you'll see 24 volts and 2 amps per phase. They couldn't change their electronics. Very expensive, fully integrated system with controls, and a lot of engineering required to redo that. In going into a new product and designing a new system, they tried many different motors, and when we were approached, we were asked, we used a similar process as I described before, varying the torque and varying the torque by varying the voltage or the current. We found that they only needed 10 ounce inches at their operating speed, and then we increased the efficiency point up to 1,000 pulses per second to give them torque at the high end. So basically without changing the voltage and the current, we reduce the torque at the low end of the speed and increase it at the high end of the speed. Okay, so that's what we're doing, is we basically change the efficiency point of the motor by changing the windings. This is a graph of efficiency of the first motor and the second motor. The first motor was running at a efficiency point around 3 RPS and the second one around 7 RPS. Without changing the motor frame size or the length, you can get different efficiency points around different operating points. And that's a very effective way of increasing performance out of an existing system without doing a complete redesign. Now, some customers ask, well, what if I wanted a motor that had increased torque throughout the entire operating range instead of just at one particular efficiency point? This is where you'd have to go through a completely new construction. So what we have here is the XT, or Extreme Torque series, by Lin Engineering. And at the curve here, you'll see that the green, orange, and red and purple ones are the torque speed curves of the standard motor industry, including our previous designs. Now, we came out with a new design that was able to increase torque by as much as 35% across most of the speed range, and even into the higher ranges, you're getting more torque. So if the application requires more torque throughout the entire speed range, you can go to a completely different design. Okay, we'll get into a case study later. I'm going to turn it over to Mindy Chang, and she's going to talk about methods of reducing resonance.
Thank you, Ryan. Now, every step motor has a resonance spot, and the reason is because as step motors move one step at a time, it actually oscillates back and forth until it finally settles into that position. And these oscillations will add up and resonate throughout your mechanical system. But what we can do today is basically explain to you some tips on how to reduce resonance or to shift that resonance point to a different speed location. One method is to change your voltage or current. Now, this is the voltage and current going into the system. When you increase or decrease these values, your resonance spot will change to a different speed location. So if you're operating at about 1 to 5 RPS, for example, you may vary the voltage and current to try and shift it to less than 1 RPS where you're not operating, and hopefully you will try to avoid the resonance spot. Another method is to change your inertia of your load. An easy way to do this is to simply add a damper onto the rear side of your motor. That's increasing your inertia, and that'll also shift the resonance to a different operating location, and this proves to help in most applications that we've seen. And if you have the capability of increasing microstepping, this will actually reduce resonance across the entire speed range. And the reason for that is because microstepping is forcing the motor to step at finer increments, and those oscillations get smaller and smaller as you get finer resolution. So this can help across the entire speed range. And if none of those work, it could be that you need a different motor. In most cases, we've seen users choose a motor that is too much power for the job. Some people worry about not having enough torque, and they oversize the motor, and this could actually cause more resonance, and it could be that you need a smaller motor. Now, Lin Engineering has developed a motor called the Signature Series that inherently within the design actually helps with smooth motion and decreases those resonance points. And we did a product comparison with a standard motor out there in the market. And if you notice, these graphs will show on the x-axis the speed. So we're basically accelerating the motor from 0 to 0.5 RPS, and then we measure the vibration amplitudes. On the right side, the competitor's motor, the red graph shows several peaks, and those are basically the resonant frequencies showing the first order, second order, and third order amplitudes. And if you notice the motor on the left side, the blue graph, those peaks are much smaller, and the very first major peak is only 0.4 in vibration amplitude, which is much smaller than any of the peaks on the right side. So if any of those prior tips don't work, it could be that you need a different design that is specifically made to create smoother motion and less vibration. Now, just to summarize what both Ryan and I have talked about, Ryan was basically mentioning you can find your torque by varying your current or voltage. That's one simple way to get the correct specs. And every motor can be maximized for the best performance for max efficiency. There's definitely one motor for the job, the right motor for the job. And finally, reducing resonance, you can change your voltage, your current, your microstepping, or your load. Now let's take a look at some example applications. On the left side, you'll see a microscope stage. And in this example, there are 2 step motors that are used to move the X and Y stage. This also has encoders, so it feeds back to the system. Of course, this type of application requires precision and high accuracy. Another example on the right side is a syringe pump. The step motor is located on the top and back side of the unit, and it rotates that round circular device. Now let's take a look at some common enhancements. You can enhance your step motor by adding a gearbox to the front shaft of the motor. This would be needed if you need lower speeds or higher torque. This gearbox has gearing inside. For example, if it's a 5-to-1 gear ratio, that basically lowers your step motor speed by 5 times while also increasing the torque by about 5 times. Another enhancement is dampers. We mentioned that briefly to reduce resonance. And it's very simple. If you have a rear shaft on your motor, you just simply add it onto the back, and it can help reduce resonance. And finally, encoders. Position verification and correction is what you would use for encoders. And I will now hand it off to Ryan to explain when an encoder is needed, and he'll go through a case study.
Hi guys, this is Ryan again. Okay, so an encoder would be used in situations where, let's say you're designed for a particular torque range, and your application, the end user, may exceed that torque design point. So if that's the case, then you definitely want to have an encoder to know when you've gone above and beyond that design point, so that if there's a stall, that you could know about it and then make a correction for it. For example, in the medical pump here shown in the bottom, if the valve is at the top, the circular device is just a valve, if it is pushing different types of fluids and crystallizing, then you definitely need an encoder to break away that torque, or if you know that the system is stalled because of crystallization, which is outside of the normal design point of that unit. Other examples are in solar and semiconductor. If there's a 90-mile-an-hour wind that's coming for it, but you only designed for an 80-mile-an-hour wind, then you definitely need an encoder to help you correct or help the system understand this is beyond the design point, and we need to make a correction or a reset or do some other action. Okay, and that's when you need an encoder. In this example here, a case study is about a medical device that you used to remove mucus from a patient's airway. So in this case here, it is a insulfate, or allowing the patient to inhale. And air is coming in through the exhaust, and if you follow the pathways, it passes through a valve at the back end. A motor and an encoder is being used to change that valve. And in this design point, it is blowing air into the patient. Okay, so in this application, high holding torque is required because a lot of airflow, and if any airflow is being checked away from that valve, then you're going to have bleed off on that airflow, and you have less suction or inhale or exhale from the patient. Okay, so the valve moves at a certain 90 degrees, and you'll see a different flow. And in this example, the customer was able to successfully use an encoder and a stepper motor to be able to hold the position for the 2 cases and you definitely don't want to have bleed off of flow while you're working with a patient. And so it gives them ultimate reliability. If there's something wrong with the system, it'll give them feedback. They can reset it, and it won't affect the patient at hand. Okay, so that concludes the Lin Engineering portion, and I will introduce now Josh Barton and Jim Stevens at US Digital.
Thank you, Ryan. This is Josh. This is Josh here, and Jim also here from US Digital. Great job on the application examples, explaining when an encoder is needed. I heard Mindy say earlier, precision and high accuracy, and really think of those terms, precision and high accuracy, for feedback. There are some key things to look at as far as decision criteria when selecting an encoder. You have to look at the mechanical specifications of your motor, the resolution that's needed, whether or not you need a home position or an index, whether or not you need a differential output or single-ended output, which is the most common. So let's look at mechanical first. Common application for encoders, obviously, is stepper motors. Here we have some Lin Engineering stepper motors with some US Digital encoders assembled. We have anywhere from a NEMA 17 motor there down to a NEMA size 11 motor. Details when thinking about mechanics. You're going to need to know the frame size of your motor. Common industry standard is the National Electrical Manufacturer Association, or NEMA size motors. Again, motors that go from size 8 up to size 34. Also, the shaft diameter is very crucial. We can offer a shaft diameter ranging from 2 millimeter on up to 1 inch. But it's key to know what shaft diameter you need, otherwise we cannot select the correct encoder for your application. And then what mounting bolt circle do you need to use? Common standard is 0.750 inches, or we can even go up to a 1.280. Depends on what you're looking for. And then obviously environmental considerations, whether or not you're in a dusty environment, whether or not you're in an environment with high noise or even moisture. Those are all considerations when looking at the mechanical side of selecting an encoder. Next, we're going to go to resolution, and Jim Stevens is going to cover this portion.
Thanks, Josh. So indeed, after you've determined which mechanical package you need in terms of an encoder, the next thing to think about is your resolution required for your application. And resolution is nothing more than just the number of increments you're going to divide your circle into as your shaft or your motor rotates in a full rotation. So the next slide, you can see this is a real typical transmissive encoder disc, where that it's composed of a series of bars and windows, which generates the resolution of the encoder. In this case, this is a transmissive system where light actually shoots through the disc and images the disc onto a sensor. Okay. And once again, this is also an incremental encoder, which is just a relative product as opposed to absolute. So next slide is just a real typical, just to show you a real typical encoder read head. A read head contains a light source, like an LED, and a detector. Okay. So in this case, is a real classic encoder system where we have a disc engaged into a read head, which has the light source and a detector, basically shooting light through the disc, imaging once again the disc image onto the detector of the encoder circuit. So the output of this, the electrical output from the encoder, is a set of square waves. The square waves are relative to the number of lines and windows on a disc. Okay, and very typically you have two squares coming out called quadrature waveforms. And you can see from this picture, these waveforms are offset by 1/4 of a cycle. And when you look at one full cycle, you can look at both waveforms together and you can determine 4 different states, okay, which are called quadrature states.
And one common misconception in the industry is CPR versus PPR. In CPR, you have cycles per revolution. PPR is pulses per revolution. An example of this would be if your application needs 100 lines, but you need an output of 400 pulses per revolution, you would select a 100 CPR encoder. So again, the cycles per revolution, 4 times, you get the PPR. And this is a misconception that we hear often here at US Digital. Customers will call in and say, I need 100 PPR, and really what they mean is they need 100 CPR with a total output of 400 PPR, or pulses per revolution.
So another piece of pretty cool information to get from incremental encoder signals is you get direction rotation information. In this slide, you can see that the top channel A, the rising edge of channel A, is leading channel B, so the shaft is rotating in a particular direction. Now, if you were to reverse this shaft rotation, you will see that the phasing changes between the incremental signals. And you can see that channel B is now leading channel A. So indeed, you can determine, from your incremental signals, direction of shaft rotation. So the takeaways, things to remember about quadrature encoder signals is that indeed, just like we said, it provides direction of shaft rotation, and that you can really also enable a 4x resolution increase over your disk CPR. Like Josh is saying, if you have a 100 CPR disk, you can get 400 positions out of your incremental encoder with quadrature signals. And something else to remember also is that regardless of your mechanical package, your encoder could be square, it could be round, it could be rectangular, whatever, the incremental signals coming out are for the most part, very standard. So the next thing to consider when inspecting an encoder is if you require a third channel index. And the third channel index is just simply that. We have our good old output A and output B quadrature signals that we looked at previously. And now we have a third channel, which is a blip, a single blip or single pulse. And an index pulse will essentially just be that. It's one mechanical location on the shaft rotation of your encoder. Okay, and that it gives you one absolute position for the shaft rotation.
Hey, Marshall, we're getting a little feedback here. I don't know if someone's phone is on, but we're having a little bit of feedback on our side. Okay, we'll continue.
Well, let's move on here to the next slide here. So index. So third channel index, if you look at the optical encoder disk, transmissive disk again, once again you see that the outer diameter of the disk is your A and B channels, and the inner tracks compose the index. Those tracks actually generate the single pulse per rotation. So really the takeaways now for encoder third channel index is indeed it's a once per rotation signal. It gives the absolute position in that rotation. So mechanically, you know when the index occurs, you're at exactly the same location. And a lot of times an index is used for a home or zero location in your system design, as opposed to using a mechanical limit switch or some other type of device to provide a single pulse indication.
And one thing just to mention on this part is when you're selecting an encoder and you need an index marker, there is an additional cost for that. So that's something to take into consideration when looking for an encoder. It does provide a little bit of a difference in price.
So the next thing you have to consider if you're speccing an encoder is what type of out circuit you require. Two types of outputs right now are very common are differential and single init. So as you see in this slide, the differential output, we have our good old A and B quadrature signals, as we've seen before. But now we also have another set of signals, which are just the opposite of the A and B signals, or sometimes they're called complementary signals. So in this case, the channel A is composed of 2 signals, channel B is composed of 2 signals. So your cabling would actually have 4 wires to generate A and B signals. And also true is that if you have an index pulse option in your encoder and it's differential, you also have 2 more lines coming out for index. And once again, the differential signals, the reason for a differential signal is that if you're transmitting in a distance, a long distance, or have a high noise environment, you require differential signals. Next slide here. So differential signal takeaways, it buys you high noise immunity. So if you have a welder running in your application and you're trying to transmit some signals, encoder signals to this application, more than likely you require a differential signal.
And one kind of practical thing is really, it depends on your environment and the noise in your environment. But for the most part, a good rule of thumb is if your lines are going to exceed 6 feet in length, then we would probably recommend a differential output on your encoder.
Another thing, too, about differential signals, like we mentioned before, is that if you're transmitting over a long distance, differential is the way to go. Lower left picture here, and this slide, you can see a concentrated solar application. This application uses encoders with differential signals to transmit signals back to a control system, which is several hundred or even 1,000 feet away. In this case, differential is the only way to go, the only way it makes sense. And something else to remember with differential signals is that, indeed, if you spec an encoder of differential signals, your controller, your receiver, has to have a differential receiver in order to take advantage of the benefits. So the next output option, a very common option, is a single-ended quadrature output. And this is the output we've looked at many times in this presentation. We've got output A, output B, and index. And this one's it's really a simple output. It's just a single wire for each output. Kind of a rule of thumb for single-ended, if you're up to 6 feet, maybe 12 feet, depending on the environment, you can get away with a single-ended output. And so the takeaways for single-ended encoder signals, it's a simple interface. It doesn't require a whole lot of electronics on the receiver side to read the signals. It's the most common form of encoder output you'll find. And it's suitable for short distance transmission. And it's all a function of your environment. If you're in a lab environment, you can increase the distance of transmission of your single-ended signals.
So when thinking about making a decision, we covered mechanical, we covered the resolution that you need, your system needs, we covered index and your home position. We also looked at the outputs, differential versus single-ended. And then at this point, you're ready to make a decision on which encoder to select. One thing to keep in mind when thinking about Lin Engineering and US Digital is flexibility and customization. Here's an example of a custom ARM encoder. At US Digital, we're able to make minor or major modifications to your applications, really based on your needs and what you're looking for. Here's a custom mounting that we did for one of our customers. And then finally, here's a custom pinion gear encoder. And really, this encoder was designed to be mounted not on the motor, but next to the motor due to some space constraints. And really, it's designed to mount next to the motor with a gear on the motor shaft. So finally, some really value propositions for us. And I'm going to let Ryan Lin jump in here in a minute. But short lead times, getting it to you quickly, personal customer service, great value for a great a product, a reliable product. And then really, a lot of companies try to fit their customers into a box and say, here's what we offer. This is the mechanical frame you get. This is the resolution we have. At US Digital and at Lin Engineering, we're looking to provide you with solutions that meet your needs. And with that, Ryan, I'll turn that over to you.
Yeah, thanks, Josh. Yeah, we parallel the similar philosophies, and couldn't be said better. So there was actually a question that came up during your presentation, which was, can you explain the difference between an encoder and resolver, advantages or disadvantages?
Good question. So an encoder provides you direct digital outputs from your application, essentially. Whereas a resolver, if you rip a resolver apart, it looks a lot like a motor. It has a windings, and it generates an analog signal, which then has to be converted into a digital format. Okay, but in application-wise, resolvers are robust, absolutely robust. If you have a high temperature, you have a dirty environment, just an extreme environment, resolvers are a good choice. Okay, the thing you trade off with resolvers is that your position accuracy may not be as good as with a digital encoder. So once again, it's a trade-off, accuracy versus environmental. But sometimes you're driven to one direction or another. Excuse me. And if your environment is extreme, resolver may be the only way to go. and it will give you position information.
And again, here at US Digital, one thing to mention on that is we do offer a magnetic encoder solution that might be a good fit for an application where there is a lot of dirt or a rough environment. So keep that in mind. We do offer some magnetic solutions as well.
We have a question here from one of the attendees, and this question is, how does amp per phase correlate to the current requirements for your DC supply? Is this a direct relationship?
Leslie, I think we're going to need you to repeat that question. Could not understand.
Okay, I'm going to try this again. How does amp per phase correlate to the current requirements for your DC supply? Is this a direct relationship?
Hello, this is Ryan. Huh? Oh, this is a, if the amps per phase correlate to current requirements for DC supply, so if you have a 1 amp per phase winding, you want to have a current power supply that is 1.4 times that for your DC power supply. Hope that answers the question.
Yeah, I'm sorry for the technical hang-up. I think Leslie's audio is out, but there's another question that came in that what's the most likely failure modes of encoders?
Most likely failure modes. Depends on the technology. If you're talking optical encoders, you know, common failure mode is that's a good question.
Environment. Could be.
It could very well be environment. You know, suppose you have a situation where you have a lot of moisture, and the encoder is not very well sealed against moisture. You know, moisture going inside the encoder could cause issues with the optics, the transmission of the pattern through the disk. Some other failure modes with encoders is if you get the encoder in a very cold application and rise the temperature quickly, if you fog the disk, that'll cause issues as well. Another kind of humorous failure mode is usually a forklift truck driver. They run in the encoders and smash on the machine, so that's, regardless of technology, is an issue.
But overall, the encoders are fairly robust. I think it'd be more the environment that could cause the problem.
Yeah, it's usually environmental in terms of moistures or dirt particulates.
All right, you know, it looks like maybe a question for Ryan or Mindy. There's a question came in. How do you deal with backlash in your stepper applications? The example on the question was you've got a gearhead with your stepper motor. There'll be backlash with your gears for in your output.
Yeah, so the backlash is actually dealt with on the gear side, and we've seen some applications where there's a helical cut gear on a backlash. I haven't seen a zero backlash gearhead. I've seen zero backlash lead screws or zero backlash other devices, but not a gearhead. You can put an encoder, but then it'll still give you the backlash you can account for in the programming. That's a very simple way, but really haven't seen anything too advanced. You go for a higher precision, different types of gears, maybe instead of a spur, you go to a planetary, and that'll help in that area. But for the most part, there's no solid answer that can give you zero backlash. You can do everything to minimize it. And Mindy's feedback is find some way to design around it. Minimize it as best you can, and then design around it.
All right. And then another, back to on the encoder side, kind of maybe a variant of the question, why would somebody request an absolute encoder over a differential or single-ended?
Sure. What will happen is if you have an application where you power down, or if you lose power and you have to come back online and pick up and go from that point going forward, that requires an absolute encoder. An absolute encoder and incremental encoder, the differences being absolute gives you position regardless of power on or off. You power down, power back up, it knows its exact position. Incremental encoders our discussion here has been on incremental encoders. You have to maintain a count value of edges, essentially, to maintain position. So you power down, power back up, and if you don't back up your count position, you lose position. So you have to start over from a known home position or something like that and start your process again. So it's really driven by the application. If you can afford to restart your application at a known point, then incremental will be fine. If you cannot afford to do that, then absolute's the way to go.
A good example of an absolute application is concentrated solar power. That's where we've seen customers purchasing the absolute encoders. When they lose power, they do not want to have to cycle back to a home position. They want to be able to fire back up and start tracking with the sun from the exact point of where they are at.
All right, and then got another one on that. Do you offer commutation outputs on your encoders?
I'll tackle that one. We currently do not offer commutation outputs on our encoders. I can tell you that this is a need that we've been hearing in the industry, and we are working on it at this time. It's under development, and it's definitely going to be an exciting opportunity for us moving into the end of 2010 and beginning of 2011.
All right, and then there was a question about the differential output as it's related to long distance transmission. And could you explain a little more on how the differential signal actually boosts the transmission?
Okay, so what happens with a differential signal? So let's take a look at a channel A. So you have an A and an A naught. They're mirror image signals. So what happens is that you have a receiver that's looking for a difference in the signals. Okay. So as you transmit this signal down the line, if you go a long ways, you have a long distance, the signals tend to drop off a little bit. You're still looking at a difference. As long as you can maintain enough signal value to essentially trigger your receiver circuit, a few millivolts essentially, you'll have adequate reception. And also, as you transmit things a long distance, the further you transmit it, the larger or the more antenna area you have essentially for picking up noise. So if a differential signal, if you pick up noise, the electrical noise, it appears the same in both channels. It's common mode noise, okay? And the receiver is looking for a difference in signals, and it will reject that common mode noise very nicely.
All right, and then just to decide, I got a couple of questions here, and if we did mention it, that this webinar will have available online in a day or so for download. But another question came in is, will U.S. Digital be designing IP-rated and extreme environment encoders? I guess related to some of their competition.
Sure. Good question. So indeed.
We currently have some IP-rated encoders, especially for the solar arena. We have our T7 inclinometer. We also have a product we've released into the solar market as well, the HBA4. Our MAE3 is our magnetic encoder, which does, again, extremely well in harsh environments. We have looked at creating some sort of a boot for the back of our optical encoders. That will help, but that will not we can't really stand behind it as a strong IP rating. So, it's always a form of discussion. We seal some encoders for customers, and that helps. But really, when you get into an environment where there is a lot of environmental factors, what we find is it's very simple to get a cover that a customer then will put the encoder inside a box and seal it up, and then it becomes IP rated on that end, and it works fine. Right now, though, I can tell you it is something that is always in discussion here.
All right, and along with those environmental questions, there's a question that came in on what do you recommend for encoders in a radiation environment? It's optical. The note here, optical doesn't work after time due to the clouding of the optics.
Yeah, that's a tough environment. Indeed, the optical ones will have issues, plain and simple. It's just a function of time, as you mentioned. So you have to start looking at other technologies. You have to start looking at magnetics, maybe resolver at that point. So other technologies have to come into play.
All right, and then I don't know if this is related to a slide. It was there's a question just as far as maybe or just some clarification on what are the P and I coefficients. I don't know if that related to a specific slide, but another question came through. Does that make sense?
I don't think it was in one of the slides, but I think they are talking about PID control. Basically, the P stands for proportional and I is integral, and this is one of the most common ways to use feedback in a control system, basically closed-loop control using a motor and encoder and a controller that does this PID feedback. And it's basically adjusting the error, actual position versus, the desired position. Yeah.
All right. Hey, and then another question here for Lynn Engineering, just on the difference between holding torque and dynamic torque.
Holding torque is when the motor is not rotating and is holding in one position. And so it should be able to withstand a certain load and hold it in place. And dynamic torque is any rotational torque that it can output while it's rotating or moving. So.
All right, just looking through here. Looks like we have one other question along those lines is what effect does microstepping have on torque?
Microstepping will slightly change the torque, and we've done some studies and tests here where if you full step the motor, you'll get the max amount of torque, and when you microstep it, you lose about 5% torque throughout the speed range. So there is some drawback, but not by too much. So whether it's torque that you need or smooth motion, you kind of have to choose between the two.
Okay, and then a question come in here. What types of applications would it be better to use a MultiTurn encoder rather than an optical encoder? So another application question.
Okay, sure. That's a good question. So suppose you have an application where you have a lead screw. You have a stepper motor running a lead screw. That's a perfect application for a multi-turn absolute encoder if you need to maintain position during a power cycle. Okay, so perfect application. So and once again, optical encoders can be either incremental and or absolute.
And I'll bounce back. There was another question came, and I'll bounce back on the torque question. Is holding torque usually greater than dynamic torque?
Yes, holding torque is usually about 30% higher than dynamic torque. That's dynamic torque at the lowest speed range.
Okay, yeah. The follow-on question was, I think that was answered there.
Yeah, it's kind of related to that. Okay.
And then I guess one time for one more question here for U.S. Digital on having a single-ended encoder connected to a controller, and what can I do to increase my noise immunity with my current encoder output?
Sure. So there are applications where you have a fixed situation. You have an encoder, single-ended, and you have a controller that only accepts a single-ended signal. So what you can do is try to minimize your cable runs in terms of keeping your cables away from interference issues such as welders, such as PWM signals. Cabling should always have a great shielding. You should have a shield. You should have the drain connected to ground on one side typically. Another thing you can do too is try to drive more current through your single-ended output. Okay, noise is typically a low power event. It may have lots of amplitude in terms of voltage, but typically doesn't have a whole lot of current associated with it. So if you can drive a little bit more current through your cable, through your output of your encoder, that'll help you provide a little bit more noise immunity. Another thing you can do too is another trick is to get some kind of a push-pull output adapter that connects to your encoder, such that you can squirt current out of your encoder, or you can sink current into your encoder at a higher level than just encoder output by itself. Once again, the name of the game here is to run some current through your cable and just try to minimize, overwhelm the noise signal introduced by noise in its current level.
All right, and then just one last, I guess more maybe it's on the manufacturer, just the internally what's added or changed that makes an encoder absolute versus incremental.
So internally, in the optical system, what makes it different is the code wheel has a unique pattern on it. Okay, so the light source looks real similar, so you still shoot light through the disk. Your detector will be different in that it will image a different pattern on the disk. Okay, but many times what the difference is, it's just simply the disk and detector. You have a unique pattern on your disk such that every time it stops, every time it has a count, it's a very unique location on the disk. It's almost like if you had a bunch of different index pulses, and you're able to discern between those index pulses. But yeah, basically they're very similar except for the pattern on the disk.
All right. Well, I guess with that, we'll go ahead and wrap this up. I'll speak on behalf of Leslie Lang now, our esteemed editor. I appreciate being on. Next time we'll get the audio dialed up better. And I'd like to thank Jim and Josh from US Digital and Ryan and Mindy from Lynn Engineering. Again, we'll have this up online. We'll send everybody out an update email where you can download the presentation if you want to after this. And again, on behalf of us all and Design World, we appreciate you joining in and tuning in for another one in the Motion Control series. So thanks very much, everyone.
Thank you.
Thanks, guys.
Thank you very much.
Thank you much.